In Algebra 2, you guys worked with scatter plots. Do you guys remember the scatter plots? And then we came up with a line of best fit. Well, it wasn't really the line of best fit, but it was a line that went through at least 2 points. And we didn't really use our calculator on those. So we're going to learn how the calculator finds the best line that goes through almost all of the points. So we're going to do that, and we're going to do it not only with lines, but we're going to do quadratic models. We're going to do logarithmic, exponential, and even logistic models. Can you fit in there? Okay, so linear regression. So what this means is we're going to have a bunch of like points, right? And then we're going to find a line that goes through most of the points, okay? And that line is going to be kind of an equal amount away for each of those points, okay? And there's like a whole explanation of why this is the best fit line, but we're just going to let our calculator do the work today. Okay, so linear regression. So it says, as Earth's population continues to grow, the solid waste generated by the population grows with it. A little gross. Governments must plan for disposal and recycling of ever-growing amounts of solid waste. Planners can use data from the past to predict the future waste generation and plan for enough facilities for disposing of and recycling the waste. Given the following data on the waste generated from Florida from 1990 to 1994, how can we construct a function to predict the waste that was generated in 95 through 99? Okay, so what we're going to do is we're going to put these numbers in this table into our calculator. Okay, so I want you to get your calculators out, and you're going to hit the button that says Stat. So look for the button that says Stat. All right, and then you're going to have the button that says Edit. So do you guys see where it says Edit? Yeah, Gabby, you can grab one. So we do Stat, and then we do Edit, and we're editing L1 and L2. Okay, so these are going to be like the X values and the Y values. So for our year, we can put 1990, we can put 1991, but a lot of times we'll just start it with like year 0. So 1990 could be our year 0 if you want, so you don't want to type in all those numbers. So we're going to hit 0 and then do enter, and then 1, enter, 2, enter, 3, enter, 4, enter. Okay, and then if we want to go over to L2, we can put all those numbers in. So we have 19,358. Oops. Enter, and then 19,484, enter. 20,293, enter. 21,499, enter. And 23,561, enter. Okay, so we have both columns in. Does this make sense, how we put them in? Okay, so we get out of there, so we do second quit. So quit is above mode, so second mode. And then we go back in. So we're going to hit Stat. And now we want to calculate something. So go under calculate. So you're going to arrow over. You can see your calculator so you can see the screen when I turn off the light. It's a little dark outside, so. And what we want to calculate is a linear regression. So linear means line, right? So we want to find the line that goes through most of these points, as many as possible. So we're going to go linear regression AX plus B. Yours might just say linreg. Do you guys see it? Okay, so hit enter. And mine looks like this. It says linreg AX plus B. Is that what it looks like? Yeah, so you guys might have, it looks like X or like X list, Y list or something. Okay, it should just say L1 and L2 in those spots. Does that make sense? So just keep hitting enter, 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 and then go down to calculate and hit enter. So if yours looks like mine, then just hit enter. And it tells you that this is in the form y equals AX plus B, and it tells us what A is and what B is. Okay, so what does that mean? That means we have a line with a slope of 1,042.1, and then its y-intercept is 18,754.8. Does that make sense? Okay, so I'm going to write those down on my paper. So that's my A, and my B was 18,754.8. Man, it's hard to, 754.8. Okay. And let's write the form that was in y equals AX plus B. Or you could write M for A, it doesn't matter. Okay, does this make sense? Okay, so that's the line that's going through most of those points. So if we look at our picture, So if we go to graph, we don't see anything yet. Hang on. Let me think about it. So I'm going to go to stat plot. Did you guys see up here where it says stat plot? And we're going to do second and then stat plot. And we want to plot these points. So for number 1, I'm going to hit plot 1 on. So I'm going to hit enter, and then it's going to bring up like plot 1, plot 2, plot 3, and I'm going to hit on. And then it talks about, well, the x's come from list 1, the y's come from list 2. We can mark these as like open circles or dots. I usually just keep it as those little open circles. And then it has the different types of plots. So we're trying to do a scatter plot. So see that first one that's highlighted where it has all the dots? That's what we want to graph. And if you think about it, we can adjust our window now. But if you just hit graph, we're not seeing anything. And we're not seeing it because it's not up at that height of what, like 19,000 or 18,000 or whatever. So we could adjust the plot. Or sometimes if you hit zoom and you go down to zoom stat and hit it, then you'll see it. Does that make sense? So I went to zoom, and then I went all the way down to zoom stat, and it gives me the perfect window for the L1, L2. Okay, the reason yours has a line on it is because you have something under Y1. Okay. So for Y1, if I want to see that line that I just graphed, I put it in. I put 1042.1 x plus 18,754.8. So I'm under Y1, and I put it in like y equals mx plus b. And then when we graph that in addition to the points, do you guys see the line that goes through most of those points? That's what we want. Does that make sense? So we've now found a linear regression. Colton, you with me? All right, so does everybody understand that? Was that pretty easy? Yeah. So now we're going to do it for, we're going to do it for quadratic, logistic, all those different ones too. Just as easy. Okay, all we're doing is we're putting things in for L1, L2, and then we're picking the type of curve that we want. Okay, so sometimes, like if you were taking AP Stats, you have to determine which one is the best type of curve. So like looking at this, do you see how our points were kind of, like there was this one above, and then it kind of went like this. Maybe a quadratic might have been better, right? Or an exponential function. Okay, I'm going to tell you which one to pick though. So in this case, we decided we're going to use linear, and then we can decide if that's okay. All right, so let's try this next one. So this is going to be another linear one. Oh wait, is this the same one? Yeah, okay, so it says make a scatter plot of the data, so letting x represent the number of years since 1990. So we did that. We used a graphing calculator to fit a linear function to the data. We graphed our function of best fit with a scatter plot. And then it says, with the function found in part B, predict the average tons of waste in 2017 and 2035. So if I'm trying to find the average amount in 2017, what value for x am I going to plug in?
Oh, no, 17.
And not 17. 27, because it was 1990 when they're starting. I know, tricky. So we're going to plug in 27. So we could do that by hand. We could use those numbers that we had before, right? And we could plug in 17 here. 17, no, 27. Now I'm going to get confused. Or you can actually, if we've already put that in for Y1, if you guys go to second table, do you guys see how it says Y1 here? Y1 was our equation of our line that we put in. Okay, and if I want to adjust that number so it's 17, my calculator, I just kind of go down, not 17, 27, dang it. I go down to 27. But if you just want to be able to put in whatever number, do you guys remember how we did that before? You can do like, what is it? Second table set, and then you can make it, second table set. You can make it so your independent is ask. So I think yours probably already say ask, because we've done that once before. Mine, every single time I turn this calculator on, it resets. So I can just put in 27, and this would be the number of tons of waste. Okay, which is, if I arrow over, I can see a decimal as well. So 46,891.5. Do you guys all see that number? Do you see how I arrowed over to get the rest of the decimals? Okay. So let's write that down. So 46891.5. So that's for 2017. And then 2035, what number do I plug in? 45, right? Since 1990. and then I go up and over, so I have 65,649.3. Okay, so it says, why could our data be incorrect in the future? So tell me reasons why it might be too little. Maybe it's higher than that. Yeah, what do you think?
Well, doesn't population grow exponentially?
Ah, yes. So she's saying population grows exponentially. So if population is growing exponentially, you would expect that the waste is growing exponentially, right? But what are we getting better at?
Waste management.
Waste management, right? We're getting better at like recycling and so on. So I don't know. Maybe it is linear in the end, right? So our population is growing exponentially, but if we're doing a good job at like recycling and managing this waste and using less, right? Don't you guys feel like you use less than you used to? Like I try not to use little plastic bags. I try to use my own bags, right? So I think we're more mindful of that. Okay, so maybe it is linear in the end. I think I would need more data to decide. All right, so let's try the next one. Okay, you guys, I've told you my story about this. Do you guys remember my story when I was 16 years old with the stopping thing? Yeah. So those of you that weren't in my class last year, when I was 16 years old, I was not driving, but my friend was, and we were breaking curfew, her parents' curfew. I was going to go spend the night at her house. And she was like, oh my gosh, my dad's going to kill me. We got to get home in time. And so we were going too fast, as Manish probably is, driving to school today because he woke up late, right? So you should never drive too fast. You're new drivers, right? I don't drive too fast because I'm an old lady. And when we were 16 years old, we were going way too fast. And there was a certain stretch of road that went by a middle school. And it was late out. It was like 10:59 or whatever our curfew was. And we saw a police officer up by that school. And so my friend freaked out and she was like, oh my gosh, let's go behind the school. And there's a way to cut behind the school. And we were in her cute little red convertible and listening to Destiny's Child. No, Destiny's Child. And she turned really quickly to go behind the school, but we were already going pretty fast. So as she turned, we hit a curb. And we were very lucky that the car didn't flip over. It probably should have. And her dad, so she calls her, well, we don't have cell phones because this is before that time. That's how old I am. I mean, there were cell phones, but they were large. And we go across the street to an apartment complex and call her dad. And her dad comes, and we know that he's going to be really upset. So we come up with this whole story about how there was a dog that went in front of us. We thought we were so smart. And then her dad's a police officer, and he pulls out his measuring tape and measures the tire tracks on the ground. And he goes, you guys were going 60 miles an hour. And we were like, okay, we were busted. So we both got in big, big trouble for that. So that's how you should never lie to a police officer, especially when it's your friend's dad, because they know, based on how your tire tracks are, how quickly you were going. Okay, so that's what this is saying. So this is a quadratic regression, and it says if your speed is 10 miles per hour, then your stopping distance is 15.1. Probably not going to leave some tire tracks for that. But if your speed is 50 miles per hour, and it takes you 175.9 feet to stop, that's not good. Okay, so I don't know. It didn't really take us 175 because we ran in the curb. I don't know how he knew, but he knew. All right, so A, so draw a scatter plot of the data. So you're going to do the same thing. So you're going to go through for your L1 and L2, so see if you remember the steps. So you go to Stat, and you want to edit the list that you put in. So we're hitting Edit. And so we want to put in 10, 20, 30, 40, and 50. So Stat and then Edit.
Did I just click Stat? Yeah.
Mm-hmm. And then we want to put those numbers in. Moral of the story, what should you have done if you were running late? Yeah, you should probably just call your dad and be like, hey, Dad, I'm going to be 5 minutes late. Do you think your dad would be upset? No. So getting in an accident, being stupid, is far worse than being like, Dad, I'm so sorry, I'm going to be 5 minutes late. All right, so we're going to get out of that, and we're going to go back into Stat. And this time we don't want to calculate a linear regression. So do you guys see what I told you to use? A quadratic regression, because it's more of a parabola shape. And you could graph it if you want to see with the shape and decide what you want to use. So we're going to use quadratic regression. Did I skip it? Oh yeah, number 5. And yours might give you all those options that it gave you before. So like it might say, what are you using for x values? What are you using for y? But just keep hitting enter. And so this one gave it to me. So it says that we have y equals ax squared plus bx plus c. So it's telling me it's a quadratic equation. A is equal to 0.0508571429. Kind of annoying sometimes. And B is 0.97057142286. And then C is equal to 0.26. Okay, so we go in here. And if we want to see the scatter plot, so clear out what we had for y1 before, we can hit graph, but again, I'm not seeing anything. Remember, that's the same window that I used for the last one. So I go to my zoom, and I do my zoom stat, and I see it. Okay, and you can see it has a little bit of a bend in it. So that could be part of a quadratic equation. It could be part of an exponential as well. Or really, I mean, it's pretty close to a linear function too, right? So if you had even more data, you could really tell, oh, this is definitely going to be quadratic. This is the notes that we still have one section left in the notes. Okay, does this make sense? So let's put it in for y1. And it's kind of annoying. I feel like there's a way to paste, like some of you guys can paste that function in there. I don't think this calculator will let me, so I have to do all these numbers. I know there's probably some way. I should probably look that up in my calculator manual. Do you guys all have that? Maybe I'll give a bonus point if you guys figure out how to paste it in there, because I'm too lazy to look at my manual. Oops. All right, and when we graph, it should kind of go right through there. Pretty close, right? It worked out pretty well. Very exciting. All right, so it says A, draw the scatter plot. We did on our calculator. You don't have to actually draw it out. B, fit a quadratic function to the data. Superimpose the regression curve on the scatter plot. So we've done all that. D, use the regression model to predict the stopping distance for a vehicle traveling at 25 miles per hour. So what do we do on our calculator? Yeah, we can go to table, and we can just put in 25, right? And when we do, it says, oh, if I was going 25 miles per hour, it takes 56.310 feet to stop. Is it feet? Meters? Feet, okay. So that would be pretty far, meters. 56.310. All right, and then E, use the regression model to predict the speed of the car if the stopping distance is 300 feet. So now we're going the opposite way. Okay, a little bit harder. So you could estimate on your graph. So you can look at the graph and you can be like, oh, where's 300? But it's kind of hard. We don't have any like numbers over here. So what we can do is under our y equals, we could put 300, right, for y2. And we can find where it's crossing. Mine's really thinking. It must be above that. So I'm going to go to my window and I'm going to make it higher. See how it only went up to 200? So I'm going to make it go up to like 350. You guys with me? Do you see what I'm doing? Okay. I'm going to guess they were going really fast if it took 300 feet. Oh man, my window's still messed up. What do I need to do to my window? I need to go to the right. So for my window, I'm going to make my X max go up to like 100 miles per hour. Okay, there it is. So we have our intersection point. And so we do second trace, and you can find that intersection point just like we've done before. So we go up here, and we get right on top of that point and hit enter 3 times. So we get 67.81946. Slower than I thought it was going to be. I thought that speed was going to be like 100 miles an hour. Right, it's not. So it's 67.819 miles per hour. Did you guys get that? Yeah, and I guess that makes sense because it's a quadratic model, right? So the stopping distance gets pretty long for every little amount that you're going to the right. Okay, does this make sense? You guys still feeling good about this? All right, so there's different types of these. So we also have logarithmic. What do you guys think a log function is going to look like? Yeah.
Oh wait, no.
Like that. Yep, you were right. Logarithmic, like that.
Oh.
Yep. So we do the same thing. So you guys want to try it? I have Carson, a meteorologist, because my son Carson is obsessed with the weather. And he tells me all the time, he's like, oh, Mommy, there's a flood warning. And I'm like, oh, really? Where? And he's like, Nevada. I'm like, what? I don't know. It's not in Nevada for a flood, but he'll tell me like these random things. I'm like, okay, great. All right, so go on to try this problem, and this is going to be a logarithmic regression, so see if you can do it. So I was pretty surprised when I plotted mine because it's actually a downwards logarithm, right? So there has to be some kind of like reflection that's flipping it over. Did you guys notice that? So when you guys found your A and your B, it's A plus B natural log of X. Did you guys have that? And your A was 45 point something. So 45.78632.063. And then B is negative 6.902524.298. Did you guys have those numbers? All right, so that makes sense because that B is negative. So that means that logarithmic function, which typically, goes like this, was flipped over, so it's going downwards. Okay, so that's okay. And then superimpose the regression curve on the scatter plot. Did you guys go to your Y1 and put that in? Good. 786.32063. Oh, wait, minus. Okay, so when you graph it, it should kind of go through those points for the most part. Oh, did I forget I forgot my natural log. Whoops. Kind of important. So insert natural log. Okay. And you guys all have that? So then the next question says, use the function in part B to predict the height of the weather balloon. Oh, I did mess this up somehow. I don't know why. Okay, where's my natural log? I put it in the wrong spot. Having the hardest time getting there. X. There we go. All right, so predict the height of the weather balloon if the atmospheric pressure is 560 millimeters of mercury. So, so we're predicting the height, which is our Y value, right? If our atmospheric pressure, which is our X value, is 560. So we can just plug in X equals 560. So we do second table and we put in 560. Did you guys all do that? All right, and you should get like 2.108. 2.108. Oh, it's in kilometers. So look for your units too. Okay, did you guys look at that? Do you feel pretty good about this? All right, so try that last one, logistic regression. So logistic functions, do you guys remember what those are?
No.
These are the ones that have two horizontal asymptotes. So we have like a limit to growth. So it's kind of like a logarithmic, but not really. Okay, because it's got that left, like that horizontal asymptote on the left. So go ahead and put those in and see what we get. Okay, so you should get to the point where you have like a logistic function. So you have your C over 1 plus A times e to the negative bx. That's kind of like one of the two parent function forms for a logistic. And we have our A, we have our B, and our C. And A is in scientific notation. Do you guys see how we have times E and then negatives, or E16? Okay, what that means is it's This is the same as writing times 10 raised to the 16. So you can put it in as times 10 raised to the 16, or you can use the E button. Do you guys know where that is? It says EE, not the little e, not like natural log and E. So it's where the comma is. So you can do second and then E like that. You can see, so do second and then it's the comma button above it. It says EE. I don't know why it says EE.
To do that one?
You can, or you can do times 10 raised to the 16.
Why can't it be just e to the x?
It is not E, that E. It's different. The little e is like 2.718, right? This is times 10 raised to the number.
I like that just perfect.
Wow, I'm surprised. How handy. All right, and then we have, so that was our A value, and then we have, oh, are you saying the second time you write E?
Second, I put
Okay.
second e down here.
After the, okay, that's, okay. I think you're good. Like, this is an E. This is our little E.
Yeah.
But this, you need times 10 to the 16th or something.
Oh, I didn't even see. Okay, I messed it up. I didn't even see that e to the 16th on the A thing. An A equals.
So there is the little e too in this problem. Do you guys see that?
It's right after.
Yeah. So I need to put in negative. So I need a negative and then an x. So insert my negative and then put in my x. Whew. This is a lot. I know. The fingers crossed. Does it go through or not?
Yeah, but like.
Mine's really thinking about it. It's really thinking.
But this is.
Oh, I think I didn't do my stat plot yet. So I'm going to do zoom.
I get 11.
So zoom stat. Yep, it went through. So exciting, isn't it? The more points you have too, the better it fits. Do you guys see how we had a whole bunch of points?
Yeah.
So it kind of helps. All right, did you get it?
No, I'm just waiting.
Okay.
I would have to redo the entire thing.
That's okay. It's just your notes. It doesn't matter. All right, so C. So use the regression model to predict the population in 1975. Okay, so one of two things. So when Greta was putting hers in, she started out with 1870 as times 0. So if you're finding it in 1975, you'd have to do 1975 minus 1870 and be like, oh, I'm going to put in 105 years, right? Okay, so be careful. I used just the numbers that were there, which is fine. You can do either way. So if I just use the numbers that are there, what number am I putting in for 1975? 1975, right? So we're just going to put that in. So we're going to do second table, and we're going to put in 1975. And when I do, I get 214.052. And then for 2010, we put in 2010. So when I do, I get 304.624. Did you guys get those numbers? Okay, so it says explain why or why not you feel these predictions are valid. So it says after the Civil War, the U.S. population increased as shown. So there were other wars, right? So there was wars after it. What else could happen to the population? So once you have kind of that like baby boom, when people come back, maybe you don't have that baby boom after a while, right? There's other things that could affect it, definitely. Okay, so let's stop there.